Additive manufacturing using stacked polylactic acid and glass fiber reinforced polymer, or PLA and GFRP, promises to deliver lightweight, high-strength composite parts for the aerospace and automotive sectors. But a raw 3D printed component cannot be bolted directly onto an airplane wing or vehicle chassis. It must undergo precision post-processing, specifically drilling to accommodate assembly fasteners. When a standard drill bit tears into these stacked materials, friction melts the upper plastic layers, while immense pressure splinters the fibrous layers beneath. This occurs because the composite is heterogeneous. You are drilling through two distinct materials with conflicting physical tolerances simultaneously, which results in structural defects under standard machining parameters. Mohammed Shariel bin Ibrahim's PhD proposal aims to solve this specific post-processing bottleneck through multi-objective optimization. To evaluate the strength of this research, Renal ran the proposal through a defense simulator, analyzing it from the dual perspectives of an academic examiner and an industry consultant. This dashboard tracks our 4 evaluation criteria: the research gap, the projected industrial impact, the methodological rigor, and the feasibility of the PhD timeline. A 3D printed composite that cannot survive a drill press is effectively industrial waste. Commercial viability depends on the part's transition from the print bed to the assembly line. Let's break down the 2 materials involved. PLA is an amorphous, semi-crystalline polymer matrix. It prints easily, but it is highly sensitive to thermal changes. GFRP acts as an abrasive reinforcement fiber. It provides immense mechanical stiffness and structural strength. When attempting to drill through both, operators face a mechanical paradox. A drill speed optimized to cleanly sever the stiff glass fibers generates severe friction, which instantly melts the soft PLA matrix. Conversely, if you lower the spindle speed to protect the temperature-sensitive plastic, the drill bit lacks the momentum to cut the glass fibers cleanly. This results in brute force fiber pullout and structural delamination. Because these material constraints directly oppose one another, traditional industrial trial and error methods lead to high scrap rates and wasted production hours. This diagram illustrates the problem. The safe machining zones for PLA and GFRP have almost zero overlap. Finding the exact operational window requires moving toward multivariate mathematical prediction. Opening the academic examiner's perspective, we first assess the research gap. The current material science literature provides extensive, detailed data on the machining behaviors of standard, monolithic carbon fiber and glass fiber composites. This schematic shows the proposal's novelty, focusing on 3D printed, stacked hybrid materials with alternating polymer layers and GFRP nets. Investigating the tension between the polymer's thermal sensitivity and the glass fiber's abrasive resistance during penetration targets an unmapped area. The research gap passes. Switching to the industry consultant's perspective, we evaluate the second pillar, industrial impact. Aerospace and automotive manufacturing rely on fully assembled systems. A single compromised drill hole limits the load-bearing tolerance for an entire vehicle chassis or wind structure. Optimizing the drill parameters directly reduces burr formation and delamination, lowering expensive scrap rates. It also manages abrasive wear from the glass fibers, extending the lifespan of the cutting tools. To maximize this impact score, the candidate should explicitly quantify the expected cost or weight savings of these stacked composites against traditional aluminum components.
This proposed research completely isolates a distinct academic void and pairs it with a lucrative solution for the manufacturing floor. We move to the third pillar, methodological rigor, focusing specifically on the proposed design of experiments. The candidate employs a box-Benkin design and response surface methodology. For a nonlinear problem with competing objectives, minimizing heat generation and mechanical delamination, these are the correct frameworks. This 3D graph maps the test matrix on 3 variables: x-axis for spindle speed, y-axis for feed rate, and z-axis for drill point angle. Plotting these interactions mathematically locates the survival envelope, a precise operational zone maintaining hole integrity across both materials. The data will then be processed through an analysis of variance to calculate the statistical weight and significance of each parameter's effect on the composite surface finish. The mathematical engine driving this setup is robust, appropriately scaled, and capable of generating valid predictive models. The statistical design is robust, but the physics of the material reveal a tension with the stated scope of the testing.
Section 4.0 of the submitted proposal explicitly states, this specific research does not consider factors such as machining temperature. This diagram illustrates the problem. Polylactic acid has a glass transition temperature of approximately 60 degrees Celsius. At that threshold, the material begins to soften and warp. Preventing thermal melting in a temperature-sensitive polymer without actively measuring friction-generated heat gives the examination committee an easy target during a defense. A second issue emerges in the measurement metrics. The proposal currently lacks explicit references to established ASTM or ISO testing standards. The candidate must lock down a specific industry-compliant delamination factory region, such as dividing the maximum damage diameter by the nominal hole diameter. This ensures the aerospace industry will recognize and accept the resulting data. While the statistical design is meticulous, failing to actively track heat generation in an experiment bounded by strict thermal limits is a major gap the candidate must either successfully defend or immediately address. We turn to the fourth and final evaluation pillar, PhD feasibility. This Gantt chart maps the 36-month timeline, from experimental design through data analysis and validation. The project scope is disciplined. By restricting variables to 3 parameters, the candidate prevents data collection from extending past its allocated 7 months. Furthermore, the study relies on fused deposition modeling, CNC milling, and standard statistical software. Because these are proven, off-the-shelf technologies, there is negligible risk of the project stalling due to unproven hardware. The proposed scope and timeline represent an executable, low-risk operational plan. Bringing all 4 pillars together, we can render a final verdict. The research gap, industrial impact, and feasibility earn a pass, while the methodological rigor carries a distinct warning. The defense strategy is clear. Be prepared to provide a rigorous mechanical justification for excluding temperature data, or pivot the methodology immediately to incorporate infrared thermal imaging. Additionally, formally integrating recognized measurement standards will guarantee the required industrial buy-in from external stakeholders. Solving the PLA GFRP machining paradox establishes the technical baseline for high-volume production. It provides the data necessary to integrate these stacked composites into the automated assembly lines used by aerospace and automotive manufacturers.